Good afternoon. Good afternoon and welcome to another edition of our MTL seminars. This is my favorite seminar of the term, which is the MTL Doctoral Dissertation Seminar. This is a seminar which is given by one of our graduating or recently graduated PhD students, and this student is selected through a fairly strenuous process that always generates a number of extremely worthy candidates. So this is actually quite a difficult selection. And so today it's a real pleasure to bring you Dan Congreve, who is a PhD candidate in Mark Baldor's lab in the Department of Electrical Engineering and Computer Science. Dan obtained his bachelor's and master's in electrical engineering from Iowa State University, studying defect states in amorphous and nanocrystalline silicon. Then he came to MIT and started his thesis. And his research interests are now focused on novel applications of excitonic spin engineering, including downconversion, upconversion, and charge transfer modulation. And we will learn more about it at this presentation today. Dan's PhD thesis has been or is being extremely productive with 3 patents, 15 articles. And in fact, looking at the letter that Professor Mark Baldor wrote nominating Dan for this seminar, he said, "I believe that Dan is one of the rare few who makes unexpected things happen." So we're very much eager to learn about that. Dan's talk is titled Excitonic Spin Engineering in Optoelectronic Devices. Dan, congratulations. It's a pleasure to have you give this seminar. Thank you. Thank you.
Thanks. Whoa, that mic is good. Can everyone hear me? I'm assuming yes. I've never been accused of being quiet. So I defended yesterday, giving basically the same talk. So thank you to those of you who came to both, but I apologize because despite the title change, it's going to be basically exactly the same. So enjoy that. But today I'd like to talk about how we can use upconversion and downconversion, which are 2 processes we're developing in organic molecules to help boost solar performance for all material systems. And let me grab my clicker off the table. So basically we're going to start with a brief discussion of solar energy and why this is relevant. I'm sure this is information that is familiar to most of you in the room, but it's good to briefly recap. We're going to go over a quick basic of some of the excitonic terms I'm going to use, just because I know they're not familiar to everyone in the room. I want to make sure that we all have the same kind of ground level of understanding. From there, we'll jump into the research. We'll talk about downconversion first and how we did with that, and then what we can do to actually make that more efficient and harvest some of that energy better. And then finally, we'll conclude with a talk about upconversion, which I think is particularly interesting and pretty cool, at least from my extremely biased point of view. So this talk kind of starts with the fundamental thesis that an improvement in solar energy is good for everyone. I think that's not a point that we need to belabor with this crowd, and I don't want to spend too much time dwelling on it, but it is quite important with world energy demand skyrocketing that we find a way to get clean, efficient, non-polluting energy, and solar is certainly one of those for us to look at. And in particular here in the United States, we have some of the best solar research, solar real estate in the world in the Southwest. So there's a big advantage if we can find a way to take advantage of this. And indeed, if we look at, as a nation, how we've been doing, we can see that solar installation has been growing exponentially over the last 15 years or so, installing 4,000 megawatts of energy just in 2013, and this is despite all of the economic downturn issues that we've had over these last couple of years. So that's very encouraging. So I think the best way maybe to look at how we can help improve the market further is really to first start and understand what the market looks like. And so if we break down current solar energy technology, we can see that 90% of it are silicon solar cells, either monocrystalline or multicrystalline, and the rest are made up with a couple of generation 2 devices. So I think the best approach that we can probably realistically take at this point in time to improve the solar market is to find a way to make silicon more efficient. So to do that, we really need to understand the limitations of silicon. And to do that, we need to start looking at the sun. And what I've plotted here is the AM 1.5 spectrum. This is the spectrum that falls on the Earth. If you ran out onto Boston Common with your big solar cell and angled it just right, this is about the spectrum you would get. So to understand how the silicon solar cell works, let's look at 3 photons. First, we'll take a photon at the band gap at 1100 nanometers. We bring it in, gets absorbed, and we collect the energy pretty efficiently. You know, we got 1 electron out for every photon in. We've captured most of the light energy in the form of electric energy. Everybody's happy. However, if we look at a green photon, we again bring this incident on our solar cell. Now we excite the electron high up into the conduction band. That electron immediately relaxes to the band edge, and all of that energy is lost as heat. So this collection, even though we're getting one electron for our incident photon still, is now less efficient from an energetic perspective. And finally, if we grab a photon from deep out in the infrared, less than the band gap of silicon, and bring this in, it's not even going to get absorbed in the solar cell, and we're going to collect 0% of the energy. So clearly this is a less than ideal situation for a solar energy conversion. And if we want to make this a little bit more rigorous, a little bit more formal, you can do this as a function of all wavelengths and give us that this purple area here is what's harvestable by silicon. The missing spot up here is due to the thermalization, and this is all unabsorbed. And these two losses make up the backbone of the Shockley quasar limit, which we're hopefully all familiar with, and limits solar cells to about 33% power efficiency. But I don't think we need to be defined by that. I think we can find a way to do better. And so we turn to the process of upconversion and downconversion. And here we're just going to describe it in the most abstract sense possible. And we can imagine that we have a downconverter black box. And what this black box is going to do is it's going to take a high energy photon and rip it into two low energy photons of half the energy. It's going to do it perfectly, perfect energy conversion, perfect efficiency. Because it's a black box and we can make it do whatever we want. So we can bring in our high energy photon, split it into two low energy photons, and they can both be collected by the silicon solar cell. By the same token, we can take our upconverter black box, and this just does the inverse process. Takes two low energy photons, smashes them together, and gives us one high energy photon. So now if we take our two low energy photons, smash them together, get a higher energy photon, this can still be collected by the silicon solar cell. So if we go back to our three photons now, our first guy is still doing its thing, happy, getting collected with very efficiency. But if we grab the green photon, now instead of putting it on the solar cell, we're going to send it into our black box, get two lower energy photons out, which can then generate two electron hole pairs in silicon. Now we're energy efficient at that wavelength. And if we grab our guy way out in the infrared, we can send that into our upconversion black box, jam those two photons together to get one of higher energy, and get an electron hole pair from that. So that's also efficient. And this is really the backbone of what we're trying to do. And again, we can formalize this a little bit. We can add in an area that we can harvest by using downconversion, and an area that we can harvest by using upconversion. And if you combine these two processes and we make the perfect solar cell out there, now we're talking not about a limit of 33%, but a limit of 48%. So the gains are very real if we can find a way to make this happen. And basically the whole rest of my talk is going to be detailing how close we are to making this happen and the processes that we can use. But before we get any further into the actual talk, I just want to give a brief definition of some of the terms we're going to be using throughout this talk, talking about organic spin states. So if we remember back in our chemistry classes way back when, a bond in an organic molecule is made up of two electrons, one spin up, one spin down. Now what we can do is we can bring in a photon of light, and we can excite one of the electrons into a higher energy position. And we call this an exciton because this hole left behind here and this electron, unlike in silicon, is still bound by much more than kT, and this will actually move as a quasi-particle. The electron and the hole hop together. And furthermore, this can interact with light. This can fall back down and then emit a photon. You can bring another photon, excite it back up. So we call this a singlet state or a singlet exciton, spin zero bound electron hole pair. But if we do a little thought experiment and we take that electron that's excited up here and we flip its spin around, now we've blocked it from recombining because Pauli exclusion principle tells us that you can only have a spin up and a spin down electron in a bond. So now we call this the triplet state. The triplet state cannot interact with light. It cannot fall down to the singlet state and emit a photon. It cannot go from the singlet state to the triplet state by absorption of a photon. And so these states are very long-lived. And they're also typically lower energy in organic molecules. And it's the interaction between these two states that we're going to play with extensively here to try to accomplish our goals. So again, a spin 1, because the electrons are paired, bound electron-hole pair we call a triplet exciton. So now let's dive into the down conversion part of the talk. And as a quick reminder, this is the area we're trying to harvest with this work, from about high energy UV to about 550 or so nanometers of light. And there we go. So to do this, we're going to use a process called singlet fission. And singlet fission is a process by which we generate an excited singlet state in our organic crystal, and it very quickly will fission, hence the name, into two triplet states, each of half the energy. This process happens extremely quickly in certain molecules. In penacene, which is the first material we'll talk about, it goes in about 80 femtoseconds. So it outcompetes basically every other process that's occurring in these molecules. And there are two important things to consider when we talk about singlet fission. The first is, like all processes, we have to conserve energy. So this can only happen in materials where the triplet state is half the energy of the singlet state. So that we put in a photon and generate a singlet, and then it generates two triplets, each of half the energy. We have the same amount of energy in our cell, but now it's in two individual units instead of one. You can easily compare this to multiple exciton generation, such as in a quantum dot, where you excite an electron high up into the conduction band, and then you have a reverse Auger process down to the conduction band edge. Very similar type process. But there's one important difference, and that is that we need to have spin conserved. In the quantum dot, you have very fast thermal relaxation down to the band edge that you're competing with, whereas we are spin disallowed from going to the singlet, from the singlet to the triplet state. If you recall, you can't interact between these two states. However, it's spin allowed to go from the singlet to two triplet states. So this proceeds very quickly and outcompetes everything else. This does have one downside, however. If we look at a solar cell principles, you can absorb from the valence band up into the low conduction band, but we cannot absorb from the ground state to the triplet state. So that we have to be careful to make sure that we're making up this absorption. Otherwise, what you're going to do by doing singlet fission is you're going to double your photocurrent, half your photovoltage, and you're going to get no net gain in power efficiency. So we need to make sure to make up this absorption somewhere else in the device. The last part of useful things that singlet fission will do is the rate of singlet fission will actually modulate with an applied magnetic field. And the reason for this is fairly straightforward. It's just a density of states argument. When you look at the final state of two triplets and the initial state of one singlet, how many states couple? At zero field, you have 3 states coupling. At high field, you have 2 states coupling. So you see this initial rise here, and then this long saturation. And we're going to use this extensively throughout this talk to understand what's happening inside of our devices. And this can tell you a whole bunch of things about whatever you're studying. The first is it can tell you about the presence of singlet fission. If you see this little up and then down in any type of observable, we are pretty sure that singlet fission is occurring. The second thing we can tell is we can tell which channel we're modulating or we're monitoring. Are we looking at the singlets or are we looking at the triplets? And this is an example of this here where we made a solar cell out of the fission material tetracene. When you monitor the fluorescence coming out of the cell, which I'll remind you can only come from the singlet state, we see this positive magnetic field response, which makes sense. If we slow down fission with magnetic field, you would expect to have more singlets and fewer triplets. And so you see this positive modulation in fluorescence. By the same token, if we monitor the photocurrent channel at the same time, which comes from the triplet state, we see this negative magnetic field effect. So you have slower fission, more singlets, fewer triplets, and the amount of photocurrent we get from the device drops accordingly. So this provides us a good way to kind of examine what's happening inside of our solar cell. So enough background, let's get into some of the research. What are we going to use for our metric? We're going to keep it pretty straightforward. We're going to use what's called external quantum efficiency. And for those of you that aren't familiar with this, we're going to bring in photons of a certain wavelength into our solar cell and collect the electrons out of it, and we're going to count and see how many we get. And we define the external quantum efficiency as the electrons we get out of our solar cell divided by the photons we put into it. And for all normal materials such as silicon, this is limited to 100%. You get 1 electron out for every photon in. We're also going to use what's called the internal quantum efficiency, which is just the number of electrons we get out for photons that are absorbed in the device. For some of these organic molecules, we have big problems with getting full absorption in the cell, so we can normalize out the absorption to get a better picture of what's happening inside of our actual solar cell. So we're going to build a solar cell. We're going to start with a Penasine C60 heterojunction, and this is, you can think of this as pretty equivalent to a PN junction in silicon. We're going to use our material Penasine here, which is our fission material. As I said, it does fission in about 80 femtoseconds, so with very high yields. We're going to use C60 to help break up the excitons. We're going to use the material BCP and then a silver cathode to collect the electrons, and indium tin oxide to collect the holes. So we make this solar cell, everyone's really excited, and we get a quantum efficiency of about 24%, which was extremely disappointing. This was, we were unhappy to see this. It's nothing that you're gonna write home to mom about. And so there was some loss process occurring in this cell. And what we figured was that when we generate excitons in this Penasine, they were traveling back to the ITO and recombining at the surface with the ITO, which is a big problem, obviously, because we're losing all of those excitons. So we went out and we hunted for a layer that we could put here to help block this process. And we eventually figured out that P3HT, poly-3-hexathiophene, which is an old organic PV material, served the job nicely. It has both a singlet and a triplet energy that are higher than Penasine, so whenever that exciton gets to the interface, it just has to turn around and go back. And so when we build these solar cells, now we see that instead of 24%, we saw a peak EQE of 82%. So we saw a very non-trivial increase in the EQE. And so we were pretty excited, and we ran back into our offices, and we did a whole bunch of absorption modeling, which is everyone's favorite task to do. And we figured out the contribution of each material to the EQE. And so what I've plotted here is we've actually modeled how much photocurrent each layer in the device is providing. So the Penasine is providing this photocurrent here in the purple, and the P3HT is providing the orange photocurrent. And these should sum up here. There's also a C60 one that I've omitted for clarity. But what this modeling taught us, what we figured out was that Penasine was only absorbing 49% of the light at this wavelength here, which means our internal quantum efficiency was 160%, meaning that for every 100 photons that were absorbed in the Penasine layer, we got 160 electrons out of our device. And this obviously is way above what you're supposed to get of 100%, which means that singlet fission has to be occurring, that we're getting this doubling of our initial photon energy to give us an extra 60 electrons. Also interesting that we found out was that the P3HT was also over 100%, so that the excitons generated in P3HT would jump into the Penasine, do singlet fission, and be collected with high efficiency. But we weren't satisfied with doing an absorption model. Nobody likes to hang their hat on an IQE measurement. They're notorious for being fickle and having large error bars and all sorts of stuff. So we borrowed a super K from Vladimir Bulovich and put our solar cell in a light trapping scheme that looks like this. We brought our laser light now in 10 degrees off incident, which then got 50% absorbed here in the device, and then captured the reflection with an external mirror and sent it right back into the device. And so this boosted our absorption to about 70–75%. And when we did this, we pushed our EQE up to 109%, which is the first time that an EQE greater than 100% had been demonstrated in the visible spectrum. So we're very excited about this because this sort of, in our mind, helped take singlet fission from a very interesting scientific problem to a very interesting engineering problem, where it's clear that this is actually something that could have device implications that we could take advantage of to make real engineering gains. So we've been doing all this great quantum efficiency work. We should have a really power efficient cell, right? No. Unfortunately, we throw it under a solar simulator, and we get an efficiency of about 1.8%, which is quite low, even for an organic device. And the problem for this is straightforward. Like I said at the beginning, we need to make up for that absorption, that low energy absorption, which we did not do in this cell. So basically what we've done by doing singlet fission in this cell is we've doubled our photocurrent, but at the expense of having our photovoltage, so we have no net gain in power efficiency. So we're going to have to find a way to make up for that absorption somehow in a future device design. And that's already been demonstrated by several groups, including ours. There we go. But we can examine what's going on in our device further by looking at the magnetic field effect. And really what we're trying to do by looking at this model is understand the basics of fission. Is this something that we can do with tiny little, like just two pentasines sitting next to each other? Do we need a big thick bulk layer of pentasine? Or is it somewhere in the middle? And so to do this, we looked at the magnetic field effect, and we built a pretty simple kinetic rate model. We absorb into the singlet state, and that can either directly break up into a charge transfer state and give us one electron, like a normal solar cell, or it can do fission, split into two charge transfer states, and give us two electrons, like a fission cell. And so what's important here is the competition between these two rates, the singlet dissociation and the singlet fission. And the nice thing is, as I said before, the singlet fission rate is magnetic field dependent. So we can use that to examine what's happening in our device. And just as a reminder, this is what the fission rate looks like as a function of magnetic field. And we can see a matching photocurrent change when we monitor our devices. And so we take that value at low field and saturation, and we can plot it as a function of different pentasine devices. So we fabricate a whole range of devices from those over here that have very, very, very thin pentasine, such that every pentasine molecule is sitting next to a C60 molecule. And we go all the way up to here, where we have this huge, big, thick slab of pentasine that's very far away from any C60. And the idea here is that we can modulate these rates by doing that. In other words, when you're close to the C60, you expect exciton breakup to be extremely quick, whereas when you're far away, you expect the effective rate of singlet breakup to be extremely slow. And so if we think about that for a magnetic field effect, here at the very thin layers, we expect all singlets to break up and none to do fission. So we expect to see no magnetic field effect. If you change the rate process of something that's not happening, you don't expect any change in your output. By the same token, if we use a really, really thick slab of pentasine, we expect no magnetic field either, because everything has plenty of time to fission. You know, if we give it 2 hours to fission, it doesn't matter if it takes 5 minutes or 6 minutes. They're all going to do it either way. And so at both ends, we expect a zero magnetic field effect. It's only in this middle here that we expect to see an appreciable magnetic field effect. And in fact, that's exactly what we see from our devices when we fabricate this whole range here. We can take our model and we can transform this into a triplet yield or an output yield. And we can do that pretty easily. And so what we see here is quite interesting. This is just the number of triplets that we get out per singlet that we put in. At very thin layers, as we expect, we get almost no triplets out because all the singlets are breaking up. But by the time we hit about 5 to 7 nanometers thick layer of pentasine, we've now basically gotten all of our triplets out. So that's kind of the floor of pentasine thickness that we need to really be doing effective fission. And we can further take this and turn this into an internal quantum efficiency. We can build a ceiling here just by assuming you collect everything. And then when we look at our devices, we see a curve that looks something like this. You lose about 40 points of internal quantum efficiency, but in general, you trace this curve, so we can see that singlet fission really is driving the physics in this device. And these tail off over here is due to diffusion losses not being able to reach the interface anymore. And so finally, we felt like the first example that we showed, the 109 EQ, was a little bit of a stunt using a bunch of external optics with a laser. And so we set out to see if we could increase the absorption. And so Vinod Menon, a visiting scientist from CUNY, had the great idea we could use a DBR to increase absorption right at the peak pentasine wavelength. And so when we did this, we saw an EQE that spiked all the way up to 126%. So for every 100 photons we put on our device, we were getting 126 electrons out. And this was a pretty exciting result, and we were pretty happy with this because now we're not doing any type of trickery. It's just an incident light beam onto a device structure, and we were pretty happy. But from there, we kind of looked at things and we realized that maybe breaking things up into charge wasn't the best way to go. The solar cell, despite having all sorts of huge quantum efficiencies, was only 2% efficient. And that gets into a lot of the problems that organic PV traditionally has, such as voltage losses and absorption issues and all of that stuff. And so maybe the best thing to do isn't to try to fight all of those issues, which the research area has been doing for years, but to try to approach it from a different perspective. So rather than taking and breaking up those triplet excitons, maybe we can harvest them in a different way. And so that's what we look to do in this part of the project. we're going to start now with the singlet fission material tetrazine instead of penacene because the energetics play a little bit better with silicon. So we bring in our light just like normal, get our singlet exciton, and this fissions into two triplets. Now, as we said in the beginning, these do not emit light. So if we just let them be here in the triplet state, they'll eventually, over a very long time period, recombine and be lost. So we would love to find a way to harvest these. And so Nick Thompson, who some of you may know, who's since graduated in my lab, had the great idea of why don't we try to put these into a quantum dot. And so what you could do, in theory, is you could take the triplet, you could send it into the quantum dot, and then the quantum dot could fluoresce with that energy. And so this would be, you can now see if this works exactly like we've designed it. This is the optical down converter, that black box that we were looking for. You bring in one high energy photon, and you get out two low energy photons. So we built this structure and decided to see, is this actually going to do what we hope it did? And before we built it, or part of the process of building it first, was to determine what's going on. The first thing you draw, as was drilled into me by a professor at Iowa State, is you draw the energy level diagram and see what you think is going to happen. And the important thing to take away here is that we have the tetrazine triplet, which is now at 1.25 electron volts, has more energy than the levels in the nanocrystal, so we think we'll be able to drive this in that direction where it can then fluoresce. The other important thing to take away from this is that any type of charge transfer state is energetically forbidden. To dump the electron or the hole over here would require a substantial increase in energy, and so we know that there's no charge transfer or any shenanigans like that going on. So to measure this, we did a bunch of excitation curves, and all we're going to do here is we're going to bring in light as a function of wavelength, just like in the EQE, onto our sample, and then we're going to monitor the fluorescence from the nanocrystals or from the quantum dots, and we're going to see what happens. And so when we do this, we see a curve that looks something like this. We see this long tail out here, which is just representative of the nanocrystals themselves. They absorb light, and then they eventually emit it. But what's interesting is we see these three peaks at higher energy, and these peaks perfectly match up with tetracine's absorption peak. So what this tells us is something, we don't know what yet, that's getting absorbed in tetracine is transferring to the quantum dot and emitting. So that's potentially interesting, that's encouraging. So we went a little step further, and if you normalize this for absorption, we can get what we call a relative quantum yield. So you can see out here that this is flat, and we've just normalized this to 1. What this represents is putting in a bunch of photons and getting however many out of the colloidal nanocrystal. So this no involvement from tetracine. This is just the nanocrystal absorbing light and then re-emitting it. And we set that to 1 for just making life easy for ourselves. And then if we look at where tetracine absorbs, we now see these dips. And so what's happening here is the light is getting absorbed in the tetracine, and then that's causing it to fluoresce with the dots to fluoresce with less efficiency. So we're robbing the dots of light energy with our tetracine. So even though there's some type of transfer going on, it's clearly inefficient. And this made us pretty sad. But quite by accident, we figured out the problem. And the problem is that all nanocrystals are synthesized with ligands on them. And these were synthesized with these very long, bulky oleic acid ligands. And these ligands could be getting in the way of the process, which of course is distance dependent. You'd expect it to transfer much more quickly if they're close than if they're very far apart. So these bulky ligands could be getting in the way. And I'd like to say we discovered this because we're really smart and thought about everything, but it was completely by accident. But anyways, once we do what's called a ligand exchange, we rip off these long ligands and we put on this shorter one. We saw this curve. So now you see more emission when you excite the tetracine and the same type of emission when you excite the dot only. If we normalize these, you can see the inverse curve is happening here as well. The dot is still behaving normally. In other words, we excite the dot and it emits a certain amount of light. But when we excite the tetracine and the dot, now we're seeing more fluorescence from the system. So in other words, the tetracine is doing something to make the dots more bright. So this was encouraging, and we actually pushed it one step further, went one ligand shorter, and saw an even better improvement. So the next step was to take this and model it and see if we could understand what was happening. So by fitting all of the absorption curves and the emission curves, we end up with a fit of this black dashed line here. And this corresponds to about 180% efficiency. So in other words, we're getting a factor of 1.8 bonus by exciting the tetracine versus exciting just the dots. So clearly there's something really exciting happening here. And so we can do this as a function of energy, and now we just assume that singlet fission is pretty good. We assume that's where your extra factor of 2 is coming from, and we can model the transfer efficiency. And we can see that at these short ligands, it's about 90% and tails off from there. So using these short ligands, we are able to actually demonstrate a transfer efficiency of 90%. So we can get that energy, absorb it in the tetracene, do singlet fission, transfer it to the dot with 90% efficiency, and fluoresce from the dot. So you may be thinking, wow, that's awesome. So you have this down converter black box down cold. And the answer is, of course, no, we don't. And the big problem is that the dot is only fluorescing with about 0.5% efficiency. So even though we can dump all of this energy into the dot, we're still working on trying to find a way to get it out of the dot with any type of reasonable efficiency that we could apply. And finally, just like before, we're going to stick this in a magnetic field and see what happens. So the first thing we can do is, as a check, we can use a low energy photon to excite the dot and monitor its emission. And we see no magnetic field change, just like you would expect. There's nothing really going on there. And we can excite the tetracene with a high energy photon and monitor its emission. And we see, again, this positive magnetic field effect that we talked about before, because we're monitoring the singlet states in fluorescence. And then as our experiment, we can excite the tetracene and monitor the fluorescence from the dot after it's transferred. This will tell us definitively what channel it's coming from. If it's positive again, we know we're just getting singlet transfer. If it's negative, we'll know we're getting triplet transfer. And I've kind of given away the answer by the way I've set up my axes here, but obviously it ended up being negative. So this was an independent verification that we're dumping triplets and not singlets into the dot. And there was one final little cool piece of evidence that we found, which is that we can vary the energy of the dot. By changing the size of the dot, you actually change its excitonic energy. And so we did a whole series of dots, and you could see how the magnetic field effect changes. This low energy dot here gives us the same curve I showed on the last page. Then we can increase the energy, see the same curve, increase the energy a little bit more, and we still see this negative curve. But as we increase the energy to go past the triplet energy, so that now the energy of the dot is higher than the energy of the triplet, we see this flipping of the curve. And so what we've done is, by just increasing the energy of the dot, we've completely shut off triplet transfer completely to our device. And so this is another sign that this is proceeding through the triplet channel, because you couldn't really rationalize a sign flip like this through any other mechanism. So that's really where we're at right now with those quantum dots. As some of you who hang out in EML a lot are aware, I'm currently over there a bunch trying to help figure out how we can get these to silicon efficiently, but that remains an ongoing investigation. That sounds vaguely police procedure-y, but that's okay. So now that's kind of the state of down conversion in our lab, and now I'd kind of like to switch gears a little bit and talk about something that we recently discovered, which I think is very cool, and we call that upconversion, or triplet-triplet annihilation upconversion. And what triplet-triplet annihilation is, besides a big mouthful, is the exact inverse of singlet fission. So in singlet fission, we took one singlet and got two triplets out. So now what we're going to do is we're going to take two triplets, jam them together, and try to get a singlet out. And so just as a reminder, this is the area of the solar spectrum we're eventually looking to harvest. So the energy diagram looks something like this. We need two molecules, one called a sensitizer and one called the annihilator. In the sensitizer, we're going to absorb light and turn it into triplets through a process called intersystem crossing, which happens in a small subset of molecules that we can intelligently choose. Once we have these triplet states, we can dump them into the annihilator and take two triplets and jam them together, get a singlet. The singlet can then emit light, and we can harvest the light. So it's a straightforward plan, I think. One of the big characterizations that we're going to focus on is what we call delta E, which is the energetic difference between the singlet state that we absorb into and the singlet state that we emit from. Obviously, you want this to be as large as possible. The smaller it is, the more energy you're wasting. So current state of the art, we can see a couple upconversion processes here. You can see here you excite this solution with a green laser, and it emits blue or purple. And down here, it's harder to tell a little bit, but there's a red laser coming this way through, and it's emitting yellow. And so this is kind of where the state of the field is right now. And there's some problems with it, though. The first is that in these molecules, intersystem crossing is big. It's a large energy loss, typically several hundred MeV at least. So that's just energy you don't get back, and you don't get it back twice because you need 2 triplets for every singlet. And so that kind of corresponds to, we see these delta E's, of about 0.61. So this is upconverting from like 670 to 570, which is, it looks cool, you get an awesome picture out of it, but as far as like actually turning it into something that's technologically relevant, has a long ways to go. And the other problem is that particularly eagle-eyed people paying attention will notice that these are both in solution. And that's the state of the art right now. There's been some efforts to move it into like a thin film geometry, but really hasn't been a solid demonstration of that. And obviously this is something that's not really going to be useful as a solar cell because no one wants to strap a bunch of cuvettes to the back of their silicon solar cell. So we really need to find a way to do this in solid state. And so to do that, we again turn to the colloidal nanocrystals or the quantum dots. They have much smaller energetic difference here, so we waste almost no energy in this intersystem crossing process to generate the triplets. Also, we can put this into a thin film really easily, so we can move into the solid state without any issue. And finally, we can again change their size so we can move as deep into the infrared as we want, rather than being stuck by organic molecules that tap out around 800 nanometers. We're going to use the material rubrene as our annihilator. This was the one that was glowing yellow earlier down here. And so for those of you who like pretty pictures instead of PowerPoint diagrams, here you go. We enlisted the help of a chemistry group to draw our quantum dot here, jumping over to the rubrene and doing triplet annihilation. We're going to use 3 series of dots, one with absorption peak at 850, one with an absorption peak at 960, and one with an absorption peak at 1010, and study the physics thereof. And we're going to add one more thing to the cell. Because we move to a solid state geometry, we can help to get the light out with more efficiency. So we add a small percentage, about 0.5% of this emitter molecule into our annihilator thin film, and this increases the efficiency with which this singlet actually will generate a photon. And you can see that here when we just monitor the emission from the thin film, exciting it at 460 nanometers. When we have rubrene by itself, we emit here. And when we add in this DBP molecule, we sell about 40 nanometers of energy, but we get a factor of 18 increase in efficiency. So we figure this is probably a worthwhile thing to do. So what does this look like as a device when you're finally all told and you build it? Well, we have the absorption peaks out here. And the emission looks like this when you run it. I think this curve actually is exciting at 808. But basically what it looks like is we can excite at any of these 3 peaks and generate fluorescence from the DBP at about 610. And so this gives us a delta E of around 0.83. So we're already about 25% better than the state of the art. So we were happy to see that. And furthermore, we're in thin film. But if you guys are tired of seeing plots and graphs, I brought a picture of this happening in our lab. We're bringing an 808 laser here into our sample, and you can see it's fluorescing red from the DBP and then traveling onwards. So we're able to harvest infrared light and turn it into visible light. So the final question you may be asking is, how efficient are you? And so to do this, we put it in an integrating sphere and we measure the fluorescence, and we can calculate the efficiency of upconversion. And right now it's happening at about 2.2% efficient, which when you look at the literature, that previous vial that I showed you was about 1.3%. So we're competitive with current state of the art despite moving to thin film and despite moving further into the infrared. Now obviously this is not a value you'd be too excited to see at 2.2%. A lot of work really needs to be put in to increase this value, and I think there's a lot of engineering opportunities going forward looking at the different loss processes in this cell and trying to understand what's happening. And the final bit of information we can look at is we can see how far can we push this into the infrared. So I took a device with 1010 dots on it, and we did the same excitation setup that we did previously in the other section. So we bring in a function of wavelength. Now we're doing it in the infrared, but PowerPoint doesn't have good infrared emitting arrows, so we'll stick with the visible. And we monitored the absorption from the nanocrystals. And so when we do that, we can see that we get good emission out of the nanocrystals all the way out to 1,000, maybe 1,100 nanometers. So we've pushed this fairly deep into the infrared as compared to state of the art. Now, obviously, there are some stuff that still needs to be tuned up about this system. First of all, though, you'll notice that 1100 is the bandgap of silicon, so we're not doing anything useful from a silicon perspective right now. So we need to find a way to push this further into the infrared so that the upconversion is happening at 1,600, 1,800 nanometers and coming back to 900 or 1,000. And the big hurdle in the way is just finding an annihilator molecule. That search is undergoing. We found a couple potential candidates, and hopefully we'll be updating you soon with that information. But for the minute, as a first demonstration of what's going on, we felt this was pretty good. And future efforts will also be made to kind of figure out a way to better engineer the structure to get that 2.2% number to something that's much more reasonable and something that we can actually look at as a solar solution. So with that, I'd like to conclude. We demonstrated an EQE higher than 100%, showing that singlet fission is really a very useful process for us to proceed with. We used the magnetic field to characterize thin films in the devices, and we demonstrated dextr transfer of this triplet exciton to the nanocrystal, and finally demonstrated upconversion from over 1,000 nanometers to 600 nanometers. With that, I'd like to thank a bunch of people, particularly my advisor, Mark, and Troy and Vladimir, who did a lot of this work, some of my fellow grad students, and even more of my fellow grad students. So thank you. I'd be happy to take any questions now.
We can take some questions now. Yes.
I have two questions. One, the first one's a simple one. Why is triplet-triplet annihilation upconversion not called triplet fusion?
It's just the field. That's actually a much more succinct way to put it.
Can I ask you to repeat the question for?
Yeah, the question was, why don't we call it triplet fusion, which sounds way better than triplet-triplet annihilation? And maybe we should start doing that. The field always calls it TTA, triplet-triplet annihilation, but triplet fusion actually pairs better. So.
Can you tell the details of your thin film deposition process? I'm assuming between the nanoparticles and the organic molecules that you're using. Is it a co-deposited system? Or?
Sure. So the question is, can I just provide some details on sample fabrication? And basically, we spin the nanocrystals down out of solution. So we work with Munji Buendi to get nanocrystal samples that his lab makes. And we spin them out of solution onto the glass slide, which gives us a thin layer of, depending on the application, anywhere from 10 to about 50 nanometers thick of nanocrystal thin film. And then we put it in a thermal evaporator and put our organic material on top. When it's the penacene or the tetracene, it's just a single layer. When we do it with the DBP mixed in, then we do a co-evap with those two molecules.
More questions? A question that I have is, so a couple of your concepts rely on effective fluorescence from quantum dots.
Mm-hmm.
And if I understood correctly, you suggested that this is a very low efficient process.
Mm-hmm.
First of all, what is the material of the quantum dots?
They're lead sulfide.
Lead sulfide. So how could you improve that process, the efficiency drastically, which
Sure.
is required?
So there's several paths you can kind of look at going forward. Certainly there's a lot of work to be done engineering on the dot itself, finding ways that we can take the quantum dot and make it just more fluorescent efficient. And that's really not my area of study, but I'm hoping that Munji Buendi's group will keep pushing that forward. In the meantime, we can look for alternative ways to get the energy out of the quantum dot. In particular, we would look at doing FRET, Forrester Resonance Energy Transfer, which actually can proceed much faster and with much more efficiency than fluorescence. But the challenge is then you need to get the thing that you're sending the energy into extremely close to the nanocrystal, within 5 or 6 nanometers of the nanocrystal itself. So that's proven to be the challenge. If, for example, we want to put this energy into silicon, we have to stick it right at the surface of the silicon for this to go with any efficiency. So those are really the two paths forward. We can try to take advantage of FRET, or we can hope that the quantum dot fluorescence goes higher. And actually, we're going to do both.
Mm-hmm. Excellent. More questions? Well, if not done,
Right.
Congratulations again on a fantastic research, and thank you for this great seminar.
Thank you for having me.
We have, of course, an award for you here. Oh, man. So, in appreciation for this great research, congratulations.
Thank you.
Thank you.